70 billion parameters is all you need. Executive summary. Modern 70 billion parameter models rival much larger ones because scaling shows diminishing returns, and recent advances make smaller models far more efficient. High-quality training data, improved architectures, mixture of experts' designs, and alignment techniques extract more capability per parameter. These models are also cheaper, faster, and easier to deploy, offering nearly the same reasoning and language performance as 400 billion parameter models. In short, smarter design now outweighs raw parameter count in determining usefulness. You can run 70B models on a single NVIDIA H100 that costs less than $50,000. Articles. For years, artificial intelligence research followed a simple principle: more parameters equal better performance. From OpenAI's GPT-3 to Anthropic's Claude and DeepMind's Gopher, scaling laws suggested a direct link between model size and capability. Yet by 2025, that rule has started to break down. A new generation of 70 billion parameter, 70B models, like Llama 3 70B, Claude 3 Sonnet, Mistral 8x7B, and Gemma 2 70B, achieve results that often equal or surpass far larger 400B models. The shift stems from several intertwined developments: diminishing returns from scale, cleaner and more curated training data, better architectural efficiency, mixture of experts' designs, and improved fine-tuning. Together, they've made smaller models the new sweet spot of capability versus cost. 1. Diminishing returns from scaling. Scaling laws describe performance improvements that follow a logarithmic curve. Each doubling in size yields smaller and smaller gains. A model that jumps from 1B to 2B parameters may improve dramatically, but doubling from 70B to 140B barely moves benchmark scores. Empirical data confirms this flattening. On benchmarks like MMLU, academic reasoning, or GSM-8K, math, 70B models perform within 2 to 4 percentage points of 400B models. Achieving those final points requires exponentially more data and compute, with little perceptible user-side benefit. As seen previously in computer vision, where ResNet 50 captures most of the useful signal, language modeling now faces the same saturation. The steep growth phase ends around 30 to 70B parameters. Beyond that, returns shrink sharply. 2. Data quality over quantity. The early era of LLMs focused on sheer volume, scraping trillions of tokens from messy web sources. Modern approaches prioritize curated, high-quality data instead. Current 70B models are trained on filtered web text, clean code bases, textbooks, and carefully generated synthetic data rather than raw internet noise. By feeding models higher quality information, developers make training more data efficient. A 70B model trained on 15 trillion clean tokens can learn as much as a 400B model trained on 50 trillion noisy ones. Synthetic instruction tuning has further boosted smaller models. Researchers use strong teacher models to generate billions of task-focused examples, reasoning, coding, summarization, and fine-tune smaller student models on them. This distillation transfers the reasoning abilities of large frontier models into compact ones. Consequently, modern 70B systems now perform tasks that previously required multi-hundred billion parameter giants. 3. Architectural and optimization advances. Beyond data, modern design choices have dramatically increased efficiency per parameter. Since 2021, innovations such as rotary positional embeddings, ROP, and AliBi have enabled better long context understanding. Grouped query, GQA, and multi-query attention, MQA, reduce inference costs while maintaining quality, and refined normalization techniques, RMS norm, deep norm stabilize deep transformers, improve tokenization, more balanced across languages, and better training schedules, like AtomW with smart learning rate decay, allow faster, more stable convergence. The net effect, a 70B model from 2025 delivers capabilities comparable to a 200B model from 2023. Architecture, not just scale, has become the main source of progress. 4. Mixture of experts, MOE. Smart sparsity. MOE architecture redefines what parameter count means. Instead of activating every parameter for every token, a dense setup, an MOE model routes inputs to only a few specialized experts. For example, Mixtral 8x7B uses 46B active parameters per token, yet has 400B total capacity. Different experts handle different linguistic or reasoning domains, so the model behaves like a large system while remaining computationally light. This specialization delivers near-frontier performance at a fraction of the inference cost. Thus, asking how many parameters total matters less than how many are used efficiently. A well-designed 70B MOE model can feel as powerful as a dense 400B model in most use cases. 5. Fine-tuning, alignment, and human feedback. Smaller models also appear smarter thanks to alignment tuning, processes like instruction fine-tuning, preference optimization, and RLHF reinforcement learning from human feedback. These refine a model's ability to follow directions, reason step by step, and produce safe, coherent text. Fine-tuning emphasizes practical performance rather than raw next token prediction. A well-aligned 70B model can match a raw 400B model on real-world tasks such as summarization, dialogue, and code generation. This alignment compression makes large-scale pre-training less decisive in determining end-user quality. 6. Deployment practicalities, the sweet spot. Even if a 400B model performs marginally better, it's often not worth the cost. Running it demands dozens of top-tier GPUs, high power draw, and complicated parallelization. Latency rises, and fine-tuning becomes impractical for most organizations. A 70B model, on the other hand, fits comfortably on a single high-end GPU node, like an NVIDIA H100 cluster, and can be fine-tuned for specific industries or languages. Companies value deployability and cost efficiency as much as accuracy. Hence, 70B models represent the optimal trade-off, big enough for emergent reasoning, but small enough for affordable real-time use. 7. Benchmark evidence, marginal gaps. Benchmark comparisons show the gap between 70B and 400B models has narrowed dramatically. Benchmark Llama 370 billion GPT-4, Turbo/Claude 3 Opus, approximately 400 billion difference. MMLU 83 to 85%, 87 to 90%, about 3 to 5 points. GSM 8K, Math 91%, COT 94 to 96%, approximately 3 to 4 points. Human Evil, Code 74 to 77%, 80 to 82%, approximately 5 points. MT Bench, Dialogue 8.5, 8.9 marginal. ARC Challenge 87%, 90% small gap. These few point differences are barely perceptible in daily interaction. Users care more about reliability, tone, and speed than about tiny numerical gaps on academic tests. 8. Broader impact on the AI ecosystem. The rise of competitive 70B models reshapes the industry. Accessibility. Open weight releases, such as Llama 3 and Gemma 2, enable startups, universities, and individuals to experiment without billion-dollar budgets. Innovation diversity. Because these models are cheaper to train and fine-tune, researchers can create specialized versions, legal, medical, multilingual, or reasoning-focused. Sustainability. Smaller models dramatically reduce energy consumption and hardware waste, cutting carbon footprints. Edge and private deployment. A 70B model is roughly the largest size feasible for on-premises or edge hardware, supporting privacy-sensitive and latency-critical applications. In short, 70B models deliver 90 to 95% of the benefit at 10 to 20% of the cost, making advanced AI accessible to far more people and organizations. 9. The new frontier: smarter, not bigger. With brute force scaling approaching its limits, researchers are turning toward qualitative advances rather than raw parameter growth. Future progress will come from longer context windows and retrieval augmented generation (RAG) for extended memory, multimodal integration combining text, images, and audio, parameter sharing and dynamic routing to enhance neural efficiency, hybrid symbolic neural reasoning, blending explicit logic with learned intuition. These directions prioritize reasoning and understanding over memorization. Parameter count, once the main measure of power, is becoming secondary to effective cognitive design. Conclusion: modern AI no longer depends on sheer scale. Through higher quality data, better architecture, MOE efficiency, and refined alignment, 70B models now deliver nearly all the utility of models several times larger. The extra performance of ultra-large systems rarely justifies their exponential cost in compute, energy, and deployment complexity. A 70 billion parameter model today isn't a compromise. It's the sweet spot of capability, efficiency, and accessibility. For nearly all practical tasks, reasoning, conversation, coding, or analysis, these models provide frontier-level performance at manageable cost. In essence, smaller models have become smarter, faster than big models have gotten better. The AI race has shifted from bigger is better to better is enough.